So welcome to the third video in our series on polynomials. Previously we've studied quadratic functions, particularly completing the square, and a little bit on multiplication division of polynomials. Today we're going to extend some of these ideas and state a couple of theorems known as Vieta's theorem and the remainder theorem. This is going to be our first pass at some mathematical theorems. So as a quick review, and as a way to introduce Vieta's theorem, let's try to find the solutions of this polynomial, 2x squared minus 3x minus 9. And as a further interest, let's look for the sum of the roots and the product of those roots. So let's try the first one. So we know we can multiply out. Let's divide by 2 on both sides. We complete the square. If you go through the sums, this means that eventually what we get is that x is equal to 3 over 4 plus or minus 9 over 4. And remember, this is shorthand notation for saying that there are two roots to this polynomial, the first of which is 3/4 plus 9 over 4, and the second of which is 3/4 minus 9 over 4. So those would be 12 over 4 is 3, or x is equal to minus 6 over 4 is minus 3 halves. But if you notice, when we use this, we can see that the sums, so when we look for the sum of the roots, and then later the product, we usually call the roots x1 and x2. That's going to be 3 over 2. And the product is equal to minus 9 over 2. If you like, for a quick review, remember that the quick way to figure out this is we could say a plus b times a minus b is equal to a squared minus b squared. Or you could just say that's 3 times minus 3 over 2. So let me not go through exactly the same steps, but just write down a little bit quicker for the second attempt of this one. Perhaps you can attempt this yourself. So if you like, when you're watching this video, please pause this now and go through this. What you'll find is that now that you've unpaused the video, did you do it? We get rather complicated numbers. So this is a little bit unwieldy, but what we get is that if we find the sums of these roots, that's still something simple. 3 over 2. And the product is simple as well. And what you might notice, is that the sums are related to these coefficients, taking care of the denominator as well. And then the products, let's go for this one, is related to these coefficients as well. And there's a reason for that. And that reason is Vieta's theorem. So here's a picture of Francois Vieta back in the 16th century. So the theorem says that for any quadratic equation, so let ax squared plus bx plus c equals 0 with real constants, assuming that the highest coefficient of the highest degree, so a is non-zero, and this condition that we've seen before, this is known as the discriminant, just so that there are at least one solution. So that's either two equal solutions or two different solutions. So assuming this to be the case, then the sum of the solutions is minus b over a, and the product is c over a. If we look at our examples above, in both cases, 3 over 2 is indeed minus 3 over 2, similarly here. And in our second example, we change c from minus 9 to minus 10, and in both cases we get minus 9 over 2 and minus 10 over 2 for the product. So let's have a look at what this means pictorially. So here's the intuition behind the proof. Let's say I have a quadratic with two solutions. There's x1 and there's x2. Notice that by completing the square, what we do is we view these two solutions as symmetric around the maximum or minimum. So when I add them, all I get is something which is constant. So here, if we look at the quadratic formula, what is this term? This is exactly minus b over 2a for x. And this is the y value corresponding to that. If it's not clear why this is minus b over 2a, you should go back to the previous lecture 1 where we completed the square and gave the general formula for the quadratic formula. And so what happens when I change b, if I change b, it shifts the center. And of course a is the scaling, is the stretch in this direction. So we can see that when the sum of the two solutions should depend on b over a. But what happens when I change c? Let's say that c increases. That just raises my polynomial. So here's my new solutions, the new x1 and x2. So I can see that this doesn't change the sum. But it does change the product. So as you can see from the diagram, there's very much a strong relationship between geometry and algebra. Okay, so let's do an application, or rather algebraic application perhaps. So using Vieta's theorem, that is, so here are the initial conditions to satisfy Vieta's theorem. and you let x1, x2 be the two solutions. Let's try and solve or find x2 over 1 plus x1 plus x1 over 1 plus x2. So as always, whenever you're watching these videos, it's probably best for you if you actually try this yourself first. Just pause the video, try it yourself, and come back to it. If you succeed, great. If not, you can look at the method as I do it afterwards. So if I cross multiply, simplify, what I get is let me not be lazy. Let's actually multiply at the bottom. So what I get is by completing the square here, so these two terms corresponds to just x2 squared plus x1 squared. And we still have x1 plus x2 left. And on the bottom, let's again collate into familiar terms. And what we get are, I should have perhaps said, if x1 plus x2 is equal to u and x1, x2 is equal to v, I should clarify what I really want to do, which is equal to minus b over a and c over a from Vieta's theorem. Then this thing is equal to u squared minus 2v plus u over 1 plus u plus v. So there's a question, check for 2x squared minus 3x minus 9 equals 0. So let's make an observation. So the observation is what we had above. So this term x2 over 1 plus x1 over 1 plus x2 is symmetric in x1 and x2. So there's this pattern that if you swap the two solutions, x1 and x2, you get the same overall term. And therefore, this final sum comes in terms of the sums x1 plus x2 and the product x1, x2. So in fact, x1 plus x2 and x1 times x2 generate symmetric polynomials or various symmetric functions in two variables. We're allowed to divide polynomials as well. So let's just do one more example. I actually did it above, but let's do it again because it's so important. Let's just, if you didn't follow the one above, let's just do it one more time. So let's move on now to the remainder theorem. So don't worry if you didn't follow all of that. Great if you did. As always, you'll get more practice in the actual tutorial. So for the remainder theorem, this is the second theorem of this lecture, this week. So let P be a polynomial. If the value at a particular number is 0, then, in fact, x minus a is a factor of P. And today we're going to come across our first proof of the module. So if you remember long division, we divide P by x minus a. So by long division, what we have is that P has to equal some polynomial times x minus a, and there's some remainder. And in the process, what we did is that this remainder term, which is also a polynomial, must have degree strictly less than the degree of x minus a. But that's 1, right? So a degree which is a non-negative number strictly less than 1 must be 0. So degree 0 polynomials are simply constants. And now we use our condition. We've used this condition since P of a equals 0. Then P of a is equal to Q of a times a minus a plus R of a. But that's 0. And that's 0, which implies R of a, which was a constant. Since it's a degree, R of a is 0. And since R itself was a degree 0 polynomial that's a constant, R of x must be 0. And therefore, P is actually just equal to Q times x minus a. And so x minus a is indeed a factor of P.